Continuing on in section 4.4 here, feel free to pause and give these a try if you'd like. We want to know what is the expression in factored form. So my factors here are 7, which is prime, times n times n. 21 is 7 times 3. So I put a 7 in my 7 column, a 3 in my 3 column, and don't forget that -1 is a factor. What I have common in both of them is a 7. So I take out that 7. I have a 7 as a factor in each of them. 7 is going to be my greatest common factor. I multiply by what's left, and remember each row is its own term because it came from its own term. So here I have n squared minus 3. I check to see if I can factor it any further. Here I cannot. So this is my factored form. Again, we could have looked at this right away, and if you recognized that a 7 comes out of both 7 and 21, you could have gone right there. Divided out the common 7. Kept it accounted for. You have n squared minus 3. On B, I have 3 times 3 times x times x. 3 times 3 times x. 18 is 9 times 2, which is 3 times 3. Times 2. And again, remember the -1 here. And remember with our factor trees, we only use the ends of the branches, only the prime factors. So we don't account for that 9. If we look here, what I have common is I have a 3 factor in all of them and another 3 factor in all of them. So my common factors are 9. That's my greatest common factor. I can take a 9 out of all of these things. What I have left, my first term is an x squared. My second term is an x, so plus x because it's positive. My third term is a -2. Now we check to see, can I factor this any further? I want to multiply to 2, subtract to 1. My only options for 2 are 1 and 2, and when I subtract them, I get 1. That works. So that 9 still has to be accounted for. That greatest common factor is still there. To multiply to x squared is x and x. To multiply to 2 is 1 and 2. And because we found the difference here and subtracted, we have different signs. 2 is bigger, so it gets a sign in the middle. So here's our factored form. Again, we could have gotten to the same place right away. If you recognize, you can take a 9 out of all of these. But if you only take a 3 out, guys, it's not going to be factored completely. So if we use this way, we can see that we have 2 3s we take out, or a 9. Otherwise, there might be factors that we miss. So just be very careful to double check. And once we get to here, we factor it the same way. So it doesn't matter whether you use your factor trees, your common factors that way, or you look at what's common, as long as you get to the same spot. And make sure we take out everything that's common. Here, 4 is 2 times 2 times x times x. 8 is 4 times 2. So 2 in my 2 column, another 2 in my 2 column, and a 2 with an x. 12 is 6 times 2, which is 2 times 3. So I put a 2 in my 2 column, a 2 in my 2 column, and I make a 3 column. I have a 2 that's common in everything times another common 2, which gives me 4. So 4 is my greatest common factor. I multiply by what's left. My first row is my first term, x squared. My second row is my second term, 2x. And my third row, just that 3, is my third term. Now we check to see if this factors any further. I want to multiply to 3, add to 2. My only options for 3, since it's prime, are 1 and 3, and they add to 4, which doesn't work. So this does not factor any further. The x squared plus 2x plus 3 part, we call that a prime trinomial. So the only thing we can take out there is the 4. And again, here, if you recognized, you could take a 4 out of everything, you divide it out, still account for it. 8 divided by 4 is 2, and 12 divided by 4 is 3. But you have to make sure that you get the entire common factor out. Okay, we can't just take a 2 out, it's got to be the entire 4. If we look here at example 3, we want to put this in factored form. I have a 2 in front of my x squared, and I need to get rid of that, but it doesn't factor out. Okay, I can't take a 2 out of 11. I don't have any common factors here. So what I'm going to do instead is I'm going to rewrite this problem a little bit differently. I'm going to change it. I'm going to take that 2 and I'm going to swing it to the back using our swing method and multiply by 2 and my last term instead of my first term and rewrite it, which gives me x squared plus 11x plus 24. Here I can factor. I'm going to multiply to 24, add to 11. My options are 1 and 24, 2 and 12, 3 and 8, add to 11. So 3 and 8 are what I'm going to use. Since I added here, I found the sum, my signs are going to be the same here, both positive. So I plug in my 3 and my 8. We're not done here though. Keep in mind, we changed our original problem. We multiplied by 2. So now I'm going to undo that and divide by 2 here on both pieces. We always reduce our fractions if we can. So here I get a 4, even if it only reduces part way. And any denominators that we have left, we swing to be the coefficient of our variables. So this is going to be 2x plus 3. If we FOIL this back, I get 2x squared plus 8x plus 3x plus 12. Combine my like terms, and we check back with our original. So again, it has to multiply back to the original place we started. Same idea here with b. I have a 4 in front of my x squared, but I can't take that 4 out because 4 doesn't go into 3 evenly. So instead I'm going to swing it to the back as multiplication. X squared minus 4x minus 12. Rewrite it. Now we factor this the same way we did earlier. I'm going to multiply to 12, multiply to my last, subtract here to 4. My options are 1 and 12, no. 2 and 6, yes. So here, to multiply to x squared is x and x. Because I found the difference and subtracted, my signs are going to be different. And we look at the bigger number, 6, it always gets a sign of the middle number. Now, we changed this problem initially. Initially, we had the 4 out front, we multiplied by it. Now we need to divide to undo it and bring it back to that original problem. We reduce any fraction, so here I can take a 2 out of both of those and I get 3 over 2. Here I can take a 2 out and I get 1 over 2. Any denominators that we still have, we swing out in front of the variable as a coefficient. And again, it's our denominators that we move. And we get 2x minus 3 times 2x plus 1. Again, if we FOIL back, we should get back to the very original problem. Here I get negative 4x, and I do. Feel free to pause here and give this a try if you'd like. Again, first step is always to check for greatest common factors. Here I don't have any. That 4 I need to get rid of, but I can't factor it out. So when I can't factor anything out, that's when I resort to the swing method. So here I have x squared plus 7x, and again, we swung that 4 back. Instead of multiplying our x squared, we're multiplying it on our lasts. We check now. X squared is x times x. We're going to multiply to 12, add to 7, 1 and 12, 2 and 6, 3 and 4. You bet. It both multiplies to 7 and multiplies to 12 and adds to 7. Because we found the sum here, our signs are going to be the same, both positive. So 3 and 4. But we're not done. Don't forget that we changed this problem by multiplying by 4. So now we have to divide both of our lasts by 4. Reduce if we can. If not, we swing that in front of our coefficient, or in front of our variable as a coefficient. To check our answers, we FOIL back 4x squared plus 4x plus 3x plus 3, which gives me 7x in the middle, and we are correct. Same idea here for b. Feel free to try it if you'd like. I can't take that 2 out because I don't have a common factor. 2 doesn't come out of 7. 7's prime. So instead, to get rid of my 2, I'm going to swing it to the back as multiplication. To multiply to x squared is x and x. We're going to multiply to my last at 12, add to 7. No, no, Yes. Because we found the sum here, it means my signs are going to be the same. I checked the middle. They're both going to be negative. 3 and 4. But again, we are not done here. We changed our problem initially by multiplying by 2. We undo multiplication by dividing. So I divide both of my numbers by 2. Again, reduce any fractions if we can. And if it can't reduce, or once we have reduced it, if we have a denominator left, we swing that in front. And then a real quick check here. 2x squared minus 4x minus 3x plus 6 gives me 2x squared minus 7x plus 6. And we are correct. A perfect square trinomial is a trinomial that's the square of a binomial. Take note on page 219 talks about these. So what it's telling us that a perfect square trinomial is the square of a binomial. We get it by taking our binomial times itself. A squared plus my outsides are AB and my insides are AB. When I combine those, I get 2AB plus B squared. So I can combine them to get there. And the same thing works if we're subtracting. It just changes it so that our outsides and insides are both negative. This is helpful because it lets me go from a trinomial to a binomial. As long as A squared is a perfect square, A times A, and B squared is a perfect square, something times itself. If we multiply the two together and double it to make sure the middle matches, and again, that's because our outsides and insides are the same, it's a perfect square trinomial, and we can go immediately into A with our sign B squared. Here in example 4, our first step is always to check if there's anything common. Well, we see that they're all even. So our first step, anytime we have a number in front of our x squared, is to see if we can take it out. I can take a 4 out of all of these. Or we can use our factors. And what I'm left with is x squared minus 6x plus 9. Now, x squared is a perfect square, and 9 is a perfect square. So if I multiply two of these together and double it, it matches my middle. So this is a perfect square trinomial. What that means is I can take one of my factors and my other factor from the back with my sign in the middle. So this is 4 times x minus 3 squared. We can still get to x minus 3 squared going the long way like we've done before. So if you're not comfortable with this, don't panic. We can still multiply to 9, add to 6. It's going to be 3 and 3. Both signs are going to be negative. So again, our first step anytime we see a number in front of the x squared is to see if we can factor it out. Here, 1 is prime. I can't factor it out. So I'm going to check to see if it's a perfect square. 64 is. It's 8x times 8x to get me to 64x squared. And 1 is a perfect square, 1 times 1. So if I multiply 2 together and double it, I get 16x. That matches my middle, which is perfect. I don't have to use the swing method here. I can go right into 8x, one of my factors, from the front, 1 of my factors from the back, and my sign in the middle, squared. It's a perfect square trinomial. The expression a squared minus b squared is the difference of two squares. Take note here on page 220 says that a squared minus b squared is a plus b times a minus b. And that's because my outsides and my insides are opposites. They add to 0. So I just get a minus b. So if I have two perfect squares here, 5x times 5x and 7 times 7, separated by subtraction, I know the only way that I can multiply to 49 and add to 0, I have no x terms here, so that's 0, is if I have the same numbers, just different signs. So this is going to be 5x minus 7 and 5x plus 7 in order to multiply to a negative. So it's a difference of two squares. We're subtracting them, finding the difference, so my signs between them have to be different. Same idea here. I have two perfect squares that are being subtracted. I'm finding the difference. So my signs between them will be different, and that's my factored form. And it checks by multiplying back. And here's our quick recap.